if obviously you have homework problems, you have several um, examples that I did on the board, you have slides, there's a lot of stuff that you have, but just to give you an idea. So one of the things that you should be comfortable with is if I give you something, and if I ever find a good pen, if I give you a signal in the time domain, time, you should be able to convert that to phasor domain, right? And everybody knows how to do this. Like I said, there are several problems, including the homework, and we'll take a look at them. So you should be able to do this, or vice versa. If you're given something in the phasor domain, you should be able to convert that to the time domain. Okay, so you shouldn't you shouldn't have any trouble with that. The next thing is if I give you something like this, circuit that looks like this, d of t, and I give you some resistance, or the resistor is purely inductive or purely capacitive, you should be able to find I, right? Let's see, and if I give it to you in Henry's, you should be able, or Ferris, you should be able to convert that to ohm or reactive inductance. Also, remember the relationships. It is pure, always the voltage is your reference, right? As being V. Your resistor, if it's a resistor, your IR, remember, will be in phase. Your IL will be lagging by minus 90 degrees or lagging by 90 degrees. And then if it's IC, will be leading by 90 degrees. So you should be able to do that. And when I ask to plug phasors, I'm not asking you to plug this and this, right? Remember, phasors. You should be able to draw this on the real and imaginary plane or or y-axis. So you should be able to do that. In addition to that, if you are given a circuit, say RL, RJX, T, and IT. If you find this, if I gotta give you obviously two pieces of information, you should be able to find for this your real power, your reactive power, and your apparent power, right? And this is in volt amperes. You should be able to find that. Or if I give you a circuit that looks like this, R, C, V of t, and I of t, you should be able to also, and I'm going to say, this one, remember, this one is negative j x c, so don't forget that, you should be able to convert that as well. But for that, you should be able to find the real power, and then the reactive power, remember, in this case, is negative, right? So you're going to get a negative bars. This is bars. And then you should be able to find S for that as well. And this is in volt amperes. Okay? So any combination of circuits, you should be able to compute this. In addition to that, you should be able to find the power factor. Find the power factor, which is equal to the cosine of the voltage angle minus the current angle. Remember, we call this theta, right? Just your phase angle. And you have to, once again, tell me whether this is leading or lagging. So you got to say this, right? For any circuit that you get, if I ask for the power factor, once you solve the problem and you get to that point, don't forget to write whether the power factor is leading or lagging. Let's see. You should be able, if you're given a circuit like this with a load, right? They can give you, I can give you S, magnitude, whatever value, I don't know, I can give you a power factor, leading or lagging, lead or lag, okay? You should be able to find the P and the Q for that, right? With that, in addition, remember you should be able to draw the power triangle. Um, Remember, P is the real part, so value X, J, Q is some value X, and then S magnitude, some value X, and then some angle theta. And remember, this theta, don't forget that this theta is still this theta, is the angle between the voltage and the current. So once you find, if you're able to find the apparent power in a polar form, the angle of that apparent power is the phase angle, or the angle between voltage and current. If you take the cosine of that, that's your power factor. In addition to that, if you're given something like this, right? And I give you the real power, let's say, and the reactive power, and I'll give you S, say I give you S in this form, theta, and I am asking for the P total, Q total, and S total. You should be able to do that, right? And then write the power triangles. I'm going to say P1, Q1J is 1 magnitude theta 1 plus the second, what if this is capacitive? Remember that if this capacitor JQ is negative, P is always positive. This is P2, Q2 is 2 magnitude theta 2. You should be able to find equal. When you add this P1 plus P2, and then Q1, and in this case minus JQ1 plus JQ1 minus JQ2. I'm just making it up, but you should be able to give me the total P for that, and the total in this case Q for that, assuming that one is negative and the other one is positive. But if they're both positive, you just add them. And then once you have that, you should be able to find the magnitude total, which is equal to P squared plus Q, I'm sorry, P total squared, Q total squared, square root of that, and that's the magnitude of this, and you should be able to find theta, the angle. So you should be able to manipulate that. Let's see. You should be able to find, once you have the real reactive and apparent power, you should be able to find the power factor, right? Or the total power factor, the power factor seen by the source right here. So power factor total is the cosine of theta, and this will be theta total, right? So, and don't forget to tell me whether it's this lead or lag kind of numbers with that. Let's see what else you should expect. Oh yeah, the other thing we talked about was power factor compensation, or power factor correction. So if you're given a circuit, sorry, it's like this. Say you have some resistive inductive load, and I'm gonna put a switch right here and a capacitor right here, and you have some value of R and JX. And before you close the switch, right? Here's V of T. You have obviously P Q going from here, this direction to supply this load right here. And say for instance you have a 4 power factor, you should be able to improve the power factor using a capacitor. And on that one, I gave you, when I probably solve a couple problems on the board, you might more than welcome to write on the cheat sheet the steps that you need to take. First, I can make this power, then how do I do this? Then I gotta find the new power factor. With the new power factor, I find the new angle. With the new angle, I'll find the Q that is going to be supplied minus the Q total gives me the Q of the cap. So we did that already. And this value I want it in bars or Q bars or mega bars, right? I'm not asking you to give me the capacitance in farades or ohms or anything like that. If you give me the bars that are required to compensate or to improve the power factor, that's really what I'm looking for. Um, let's see. Oh, yeah. Last but not least, and this one's, if I give you a problem like this, I will make it overly complicated. What I will do as a matter of fact, if you go to the very last set of slides that I gave you, the ones with the three-phase systems, remember I gave you the delta Ys and all that, and I'll show you. You're more than welcome to either however you want it. If you want to write it on your cheat sheet to make sure that you remember those how the angles are laid out. If you're given like face-to-face voltage, what is the relationship between face-to-face to face-to-neutral? And you got to remember the square root of 3 and the minus 30 degrees. We'll talk about that. And we'll do one problem today like that. I think there's one in the homework. But once again, if I give you this, say VA is equal to some angle or magnitude V times angle, there's some angle, I don't know, phi V, right? You should be able to find V, C, with the same magnitude, phi voltage minus 120 degrees, magnitude is the same, phi voltage plus 120 degrees, so you should be able to do that. Like, once again, if I give you this, you should be able to find the other two. You should also be able to find VAB, VBC, VCA, and like I said, we'll do a couple of problems. So this one is the one that what would probably make it easier for you is if you just sketch the phasors from the slide deck that I gave you, you should be able to do that. So you should be able to understand those relationships. And you should also be able to plot them, right? So you should be able to, if I ask, well, I want you to plot those, you should be able to say VA to neutral, say VB to neutral, and BC to neutral. I'm going to assume this minus 120 plus 120, all that. So, and what I find sometimes, I don't know it, and I don't take a lot of points for this kind of stuff, but I find it when I ask for the phasor diagram, people either they're doing it too fast or they forgot, and they will write something like this: V of VT, VA of T. No, that's not it. This is a sinusoid. That's not a phasor. So don't get confused. I will not ask you for sinusoids that I won't ask you to plot any kind of sinusoid. The only thing that I won't ask you, oh, yes. So, normal test. I want to ask you to plot this. I won't ask you for waveforms. The other thing I won't ask for is this. Remember? Remember that? I won't ask you for anything like that. I won't ask you for instantaneous power. Obviously, you should be able to know the equations, right? P is equal to 3V line to neutral, I line, cosine theta. If you're given line to neutral, and if you're given line to line voltages, this is square root of 3V line to line, I line, cosine theta. And then for Q is equal to the same thing, right? V3, I'm sorry. And this is for three-phase systems. V or J is equal to square root of 3. Oh, sorry. I'm going to erase this. 3 times, again, V line to neutral. That's what there is a 3. I line, sine, theta. And if you have the line-to-line voltages, is J square root of 3, V line to line, I line, sine theta. And I will write all these equations on my cheat sheet so that you have them right in front of you. And once you have the real power and the reactive power, you can find the apparent power by taking the square root of the squares. You can find the angle. We already have the angle, which is theta, the angle between the voltage and the current. But once again, I will not ask you to plot this. I will not ask you for instantaneous power. What I will ask you for average powers, you should be able to use those equations and know when to use which one, right? Know when to use 3 versus when to use square root of 3. And the one thing that I want you to remember is if the voltage is given to you as line to neutral, then you use 3. If the voltage is given to you as a line to line, then you use the square root of 3. Now, what I said was, if I give you any problem and I tell you a three-phase system consists of a voltage source of whatever voltage, and I don't tell you whether it's line to line or line to neutral, remember, it's always line to line voltage, always. I don't have to tell you it's line to line. The only thing I have to tell you, and you know how it's line to line, is I tell you it's a three-phase source. However, if I said a line to neutral voltage, I'm telling you line to neutral. Does that make sense, everybody? Let's see. What else? I think that's pretty much it. It should be a very simple test. Like I said, I'll do some of the homework problems so that you feel more comfortable with this. So if it's not on the homework, if it's not on the slides or the lecture notes, you can come back to me and say, no, I'll get my 3 points because you did not say that you were going to cover this. So, but everything that I cover is after game. Any questions, anybody? Everybody okay? You guys ready? So if I give it to you now, you'll be ready?
Yes.
All right. Don't overthink it. It's not that difficult. I think if you have your cheat sheet, you'll be okay. I was talking to somebody this week, a math teacher for primary, K to 12. It's not only a math teacher, but it's those people who specialize on helping students who have deficiencies in mathematics. And I said, you know what are your thoughts about this? And I mentioned, what are your thoughts about memorizing formulas? And she said to me, I don't know why we still ask the students to memorize formulas. I go, I agree with you. She said, that doesn't make any sense. Memorizing formulas used to be when we didn't have computers, when we didn't have, there's a lot of things that we have now for which we needed to remember, right? Case in point, I said, yeah, I remember. If somebody asked me this equation, obviously you might say, yeah, but you wrote it, you have it memorized. There's certain things that if I don't memorize, it's like I wrote it like 100 times, right? Eventually. But what I'm saying is, there'll be the days where you couldn't remember, you have to go to a book. I gotta go find the book, you go through the book. What do you guys do now? What will you do?
I asked ChatGPT to make me a cheat sheet.
Exactly. You just ask the computer for the formula. They will give it to you. So that's what I was saying. Yeah, I said there are reasons what we used to ask students to memorize things. But today I don't think it's so much about that, and it's more about, do you know how to approach the problem? Do you know when you have a good answer versus you having a bad answer? That's really at the end of the day what we're looking for. Does it make sense, right? When I get the phasors and I have a load that is resistive, inductive, and by the way, I'm getting a positive angle in reference to the voltage, I might have done something wrong. Those are the things that I'm looking, or where should be looking to test, see if you understand, but not memorizing. That's, like I said, that's the old days, and for people like me, it used to be very painful because I'm not really good at memorizing. Some of you are really good, and there are people who are really good. I mean, I said
maybe one out of, I'm gonna say 2 out of 3. Because I have 3 kids. Two of them are very good at memorizing stuff. I don't know how they do, but then when one I had the other ones like, oh, don't ask me to memorize. I don't know. So, anyways, put on your cheat sheet. Spend a little bit of time on that. And now, the other thing, and I'll do it on the board, but I expect you to probably do it on your calculator. It's just that I gave you homework. Is how to manipulate phasors, right? You should be able to do it on your calculator. It should be going the long way, otherwise, it's gonna take you a lot of time. So I give you the entire class, meaning sometimes I'm here a little early, not a lot, but 10 minutes early, and if I have the exam and you come in, I'll give it to you. Just take it, go. But I will give you the entire class. Don't rush. That's what I tell everybody. Make sure that you're at a normal pace. You should be able to solve the exam in, at a normal pace. I said an hour and a half, hour and 45 minutes. I mean, it's not that long. It's very short. But that doesn't mean that I want you to, I'll be here until 9:45. So, you have all of the time. And the only thing that I asked, and I have had this before, where students say, oh, here's the exam. And then they leave and then they want to come 10 minutes later and say, hey, I forgot this. No, you already gave me the exam. Okay, so that's what I said. Take your time, don't rush. How many problems? The class is not that large. So when the classes are very large, I usually give about between 2 problems. Like I said, the class is small, so maybe between 3 and 4. And I usually give you, meaning no less than 3, no more than 4. And for each problem, I usually break it into 25, 25, 25, or 33, 33, 33. And I give you and I tell you how many points I try to do. Like if I have 25 points, right, on this question, and I have A, B, C, D, E, so I can do 5, 5, 5, 5, 5. That's kind of sort of how I try, because it makes it easy for me to grade the exam. Um, but I'll give you the example. Like I said, oh, question number 1, 25 points, or 30 points, or 40 points, whatever the number of points. And I try to keep it also based on the difficulty of the problem. Based on the length, difficulty sounds like the problems are really difficult. No, they're just longer, right? Not difficult. And you guys know it. I mean, you guys probably already Googled it before you took the class. My tests are really easy. People say, his tests are a piece of cake. Really easy. I want you to get an A. Really, I do. I do want you to get an A in the class. And we're not cheating, right? We're not doing anything. I'm just giving you something that is normal, that you can work at a right pace, at you at the right time. Now, that being said, have I come out across C's? Yeah. I mean, it happens when somebody, maybe came and forget the calculator, or forgot to write a cheat sheet and doesn't know how to do it, right? So I do that. The other thing I made before. So if I have A, B, C, D, and E, I want you to break it down and put a box on the answer. Okay, sometimes it happens to me, and I know when we're doing things really quick, you do something and then you go, oh man, I forgot, and then you jump on the other page, and then you jump to the other page, and I'm looking for the answers that I can never find the answer, and it takes me a lot of time to find it. If you try to be meticulous, but it's most important if you box the answers at least, oh yeah, oh, wrong answer. Okay, now let me look at the process. You make it easy on me when I said, oh, right answer. Okay, it saves me time, and it helps you that you get your exam score back right away. Oh yes, the other thing that I like for everybody to remember is this: I will put a Dropbox for the exam. So when you're done with the exam, you give me the hard copy, but I also want you to take a picture of the hard copy, convert that into a PDF file. So if you don't know how to do it, practice, and then upload the exam on the computer. So that way it's easier also for me, not only to track the exam, but also to grade it. I just go to my iPad and put my notes in there now. I'll give you the exam much faster. Let's see. Da, da, da. Bring plenty of paper. Sometimes I find that people come and I don't usually, sometimes I carry paper, but sometimes I don't, and then people are like, oh man, I need paper. Let's see. Bring paper. I cannot say. Any questions? Everybody okay? All right. I think you guys are good. And if you have any questions before we leave tonight, you can ask me. Because if you mail me, chances are I won't respond back to you until we get back next week. All right, so homework number one was really simple. And like I said, you should be able to do this. There was a was it 2.1? Yeah, problem. And it was A1 equal to 5 angle 60 degrees. These were just complex values. A2 was equal to minus 3 minus J4. Um, the AC, in this case, if they're asking you to, let me see, the first one is to add, I believe. Oh no, to convert to rectangular form. Convert A1 to rectangular form. Yeah, so A1 was equal to, yeah, 5 cosine 60, right? Plus J 5 sine 60 degrees. So A1 was equal to 2.5 plus J 4.33, right? And then the second question was convert this guy from rectangular to polar, so A2 is equal to minus 3 minus J4. Sometimes this was right here. I mean, I won't ask you to do that, but if you were doing it on calculator, you're a little bit skeptical about your answer, or where the angle is, whether you got the right angle or not. Sometimes one way to do it is which quadrant? Am I on 1? Am I on 2? Am I on 3? Or am I on the fourth quadrant? Using the rectangular form is really easy to know that, right? I know I'm here and I'm here, so I know I'm somewhere in this quadrant, right? So the angle can go this direction or that direction. So sometimes the calculators they play tricks on you. Be careful on that. Uh, but basically, that's really what it is. So in this case, the magnitude, we often call that r, is the square root of the x plus the y and the square root of that. So in this case, r is equal to 3 squared plus 4 squared, right? Square root of that, and that gives us 5. And that's what I get, 5. Yeah, arc squared. And then the angle is the arc tangent of of y divided by x. That's the angle. I'm gonna call it theta. And this is the one that I was saying that is sometimes it's good if you're doing it this way, which I don't recommend. But if you, for whatever reason, forget your scientific calculator and have to do it this way, this case was theta is equal to r tangent of minus 3 minus 4 minus 3, right? Then we get equal to, this gives us about 53.1 degrees, okay? Or you can add 180 degrees and do it in the other direction, then get 180 plus 53.1, which comes up to be what, about 233 degrees, 0.1 degrees. So whether you go from this direction or this direction, obviously this one, if you go in that direction, is negative. But as I said, I will try to be able to do it on the calculator. Let's see, and then if it's been asked to do it in exponential form, A2, and we did this when we were doing Euler's equation. Let's see, magnitude of R times e to the j an angle to 33.1, right? So again, I won't ask any of that. I'm not gonna do every single one of those numbers because, like I said, that's not something that I always ask you. That's math. That's not. That's really not what the intent of the course. But I will give you the answers. I'll upload it for you so that you know how to do it. Once again, just try to do those on your calculator so that way you know how to do it. How to use calculator. Yes, sir.
But can you explain one more time why we're adding 180?
All depends on what direction you want to make it. Do you want to do it? You want to go from? You want to measure the angle from this direction, or you want to make it from this direction? I'm adding this 180, right?
Yeah.
To this.
Okay,
So,
so you
yeah.
always have to add 180 or you just leave that as
Oh,
is?
always 180.
Always 180?
Yeah. So, but the point I'm trying to make is that I don't want you to worry about that, right? Do it on your calculator. Enter the values, with positive and negative angle, and then you get the same thing. Same like, remember when I talked about this too? And I said VA is equal to, say, 1 angle 0. VB is equal to 1 angle minus 120. That's because I'm measuring the angle in this direction, minus 120. But I can say VB is equal to 1 angle 240, right? Which is in this direction. Make sense? Right? So if I enter on the calculator, if I enter the phasor 1 minus 120, or if I enter as 1 to 40, is the same thing. Okay? So again, if you are a little bit skeptical about where your angle should be, you can use the rectangular form just to line you on the right quadrant. But I don't think you're gonna need any of that. Like I said, use your calculator, try to manipulate phasors. That way, it will be so much easier. All right. Let's see. Next thing. Okay, this one, yes, these are fair problems. So if you're given signal I of t is equal to, I think it was 400 times the square root of 2 cosine omega t minus 30 degrees, okay? And they asked us to derive the phasors, to convert that from a time domain signal. So this is time domain to the phasor domain. We know, oh, okay, I know I'm gonna need this, and I know I'm gonna need this value, okay? So that in the phasor domain is equal to I RMS. Remember, this is I peak or max. I'm going to call it I max, I RMS, angle, theta of, I'm going to use phi I, and I'm going to call this angle phi I, or the angle of the current, right? I know that this is I is equal to 400 times square root of 2, that's the peak value, or the maximum value. And yes, sir.
Just a question. For the current vector, or sorry, phasor, you're always going to be using IRMS, right?
Yes.
Yeah, never the maximum.
No, this is always going to be an RMS value. Always, always, always. Never the peak. Okay? You gotta remember that. So, to remember, I max, I'm gonna write it here, is equal to square root of 2 times IRMS, right? So if I'm looking for this value, all I'm doing is dividing by square root of 2. So in this case, we have the square root of 2, that's my magnitude, and then my angle, I just take it from here, which is minus 30 degrees, right? Another way, and I know we did this derivation, right? You have it, on how we got from here, from a time domain signal to a phasor signal, where I said, oh, the only thing that we keep is the piece of the signal that doesn't move, or we freeze it, right? Another way you can see it, and I probably didn't explain it that way, is if I make this t 0, okay? So that's what I'm freezing. I'm freezing this signal when t is equal to 0. This becomes 0, so I got this angle and this magnitude. The only thing I do is I divide it by square root of 2 to get the RMS value, right? That's really what it was. So in this case, I phasor is equal to 400 because I cancel this, right? 400, angle of minus 30 degrees. And this is in amps, of course. And you should be able to convert that from polar to rectangular on your calculator, right? You shouldn't have any issues with that. That's very simple. Another signal that was given to us, I think that was problem number 8 from problem number 2.2, I think it was. They give us the signal I of t is equal to 5 sine omega t plus 15, I think it is. At least that's what it should be on the homework. Okay, so that's the problem we have here is, now, is it impossible to give a time domain signal using sines? No, it's not. There's nothing wrong with it. But I said it at the very beginning when we were going through this, that by convention, so that we don't get confused, we decide to always use the cosine function instead of the sine function. So once again, that doesn't mean if anybody wants to ever represent a current as a sine, yeah, that's totally fine. But because we said at some point we decided, and I said we decided, electrical engineers working power system, to use cosine so that we do not get all mixed up, is to make any signal that is sine, convert that to a cosine, so then I of t is equal to 5 cosine of omega t plus 15 minus 90 degrees, because this is what's making the sine signal a cosine signal, which is using just shifting it, right, by minus 90 degrees. So, and we can rewrite as I of t is equal to 5 cosine omega t minus 75 degrees,
Yes.
right? So now I have this signal, same signal, it hasn't changed. The only thing is that I shifted it to make it a cosine. So then I have I'm gonna call this, with a name, A maybe, A, that's this letter B, is equal, phasor is equal to, I have the magnitude, make this 0, minus 75, so I have 5, which is the peak value, divided by square root of 2, that's its magnitude, or the IRMS, angle of minus 75 degrees, so I'm sorry, is going to be, you can leave it, by the way, if there is, if I was gonna give you a signal like this, and and uh, and you give me this answer, 5 divided by square root of 2, that's great. There's nothing wrong with that. But if you want to make it more simple, just do the math. 5.53 angle minus 75 degrees, and this is in amps, right? So basically, once again, you're converting from the time domain to the phasor domain. Time domain sine to the phasor domain. The only thing you gotta remember that this has to be a cosine. Am I gonna give you something like this on the test? The answer is no. But you should know how to do that. You should know how to do with those kind of signals. Yes, sir.
Do we always assume in time domain they are IMAX?
In the time domain, well, let me write the general equation. I'm gonna write the general equation for that. I of t is always equal to I max
Okay, so we always assume
cosine
yeah, IMAX.
omega t plus or minus, depending on the v, right? That's the general formula. So it's always or I of t is equal, bless you, square root of 2 IRMS cosine omega t plus omega phi b, right? Same thing, isn't it? Does everybody agree with me or you? So you
Yes.
see what I did?
Yes,
So
yes.
basically, if I didn't see a square root of 2 over there, I assume this is I max.
Oh, yes, yes. Remember, that very good point. Remember, this is I max. I don't have to put a square root of 2 there. Do I make sense, everybody? I mean, to make this homework problem simple, they put a square root of 2 there, so you know, oh, I just gotta divide that by square root of 2 cos 400. But this value, whatever is in front of your cosine, is always this value. Unless we write it in this form, which is written in this form. Make sense, everybody? Okay. So, yes, and you know what? It's a good point you bring up because sometimes it does happen. People are going really fast and they see a square root of 2 and they don't know, wait, I remember the square root of 2 was under. I seen it when people don't know what to do. They come to me during the test and they said, I thought the square root of 2 was under, was divided by square. Yeah, but that has nothing to do with this. This just happens to be the I max value, okay? All right. Again, I just want you to know that I won't give you anything like this on the test. If I give you a signal, it will be in this form or in this form. If I. C, I don't think it will give you that. But I of t, oops, I of t is equal to 4 cosine omega t minus 30 plus 5 square root of 2 sine omega t plus 15. Okay, and then they want us to convert this from time, I'm sorry, time to phasor. Okay, so actually this looks funny, but is there such a thing? Yeah, I mean, you can think of what if you have two sources, current sources, like this, adding, and this piece right here is, I'm gonna call this I1, I'm gonna call this I2. Yeah, I1, I2, there is such a thing, right? It's just two current sources, that's what that is telling. There's two current sources connected to this node. This, of course, is I of t, right? It's the total. So it's not something that you will never see. No, you can see that. Actually, you can do this in MATLAB. You can. The only thing here is, once again, that we do have a sign right here. So in this case, we can rewrite it as I of t is equal to 4 cosine omega t minus 30 degrees plus 5 square root of 2 cosine omega t plus 15 minus 90, right? Yep. So again, all I did is that this source, current source, I convert that from a sine to a cosine by doing the minus 90 degree shift. Still the same signal, looks the same, but it's 3% as a cosine. Back to what you were asking me, so in this case, they're giving us, right, two ways. They're giving us here and here, right? So they're giving us that signal in this form, I max to sine omega t, and they're giving us this signal in this form, square root of 3 times IRMS. Make sense? Okay. So, with that said, let's see, we can write this as, oh, I close it because if I don't, then it gets dry. All right, then I can rewrite this part right here, as I said, and this right here now as follow. I phasor is equal to 4 divided by square root of 2 magnitude angle of minus 30 degrees, that's one phasor, plus 5 square root of 2 divided by square root of 2 magnitude, this angle of minus 75, we did this, right? Minus 75 degrees. Minus 75 degrees. So I have those two phasors. I can add these two together. Well, let's do this. I can say I is equal to, what did I get? 2.83. 2.83 angle of minus 30 degrees plus this cancels, so that's 5 angle minus 75 degrees, and then you can add this in your calculator. And then you have I is equal to, what do we get? Total, I total, if I enter that, is equal to 3.74 minus J 6.24. And there's a couple of steps here. You'll have it on the notes, but basically that's what it is. If you enter this phasor in your calculator, you should be able to get that. And if they wanted it, you can convert this to a polar form on the calculator. And then in polar form, this is equal to I equal to 7.28 angle of minus 59.06 degrees. 59 degrees is fine. Okay, so that's it. Any questions? This is simple, right? I mean, it's repetitive. Now that you know it, it's just same thing over and over and over again. The one thing is, as I said, is that I want to make sure that you remember is if they ask you to plot the phasors, don't use this signal. Remember that it's the phasors are time independent. This is what I'm looking for. That was very simple. I should be able to do this. As a matter of fact, where do we find this? Well, we find this if there's some examples, right? When I give you a circuit, or you're given a circuit with a voltage source, say you're given a voltage source and an impedance of the load, and they're asking you for the current, right? Sometimes we give you the signal or the voltage source as in the time domain. Just gotta convert that into the phasor domain. But that's the only time that I can. But I'm gonna say once again, I will not give you anything like this. V of t, like no. I just want you to know that that it can come up in your lifetime. If it does, that's what we're doing. We're just adding two current sources. That's what this is. I think I said this because people sometimes ask, but why? What will I use if I ever time domain signals? The answer is time domain signals come a lot in power systems. If you're dealing with analysis in the time domain, like electromagnetic transient analysis, we might come up with that at some point in time. In which case, you have to use the IFT and the BFTs. But also, if you're doing some sort of controls, it's better to have the inputs to your controller in the time domain than it is in the phasor domain. But people do it both ways. It's just that the time domain is much faster to react than it is in the phasor domain because you don't have to convert, it goes straight. So you don't have to worry about any kind of delay. But again, that's if you're getting to control systems. This is power system analysis. All right, the next one was problem 2.4. I think on 2.4, we're given something like this, a voltage, and then also an impedance, if I'm not mistaken, like this, Z1, and another impedance in parallel, and this was called Z2. uh, Z2. So this one was 8 ohms. Let me see, 6. So 6, yeah. J6 ohms and 8 ohms. And this one right here was minus J6 ohms. Oh, by the way, if they give you something like this, they could. There's nothing wrong with giving information like that. Somebody gives you this and says, this is 8, this is 6, and this is 6, right? And they don't tell you anything else. They just say 8, 6, 6. You have to remember that once you you get those values, you gotta remember that if it's a reactor, you put a J in front. If it's a capacitor, you put a minus J in front. Okay, but you could find that there is books, there is documentation where they can give you, oh yeah, this load Z1 is 8, 8 and 6, and Z2, but they gotta show you the symbol. That's the point I wanted to make. They gotta show you a symbol. If they put a 6 and it looks like an inductor, it's a J. If they give you 6 and looks like a capacitor, it's minus J. Or they can tell you, oh, the reactive capacitance is 6 ohms. Oh, it's minus J6 ohms. Okay, don't forget that, otherwise you get the wrong answer. So in this one, that's what they do. So they tell us that Z1, oh, and they're giving us this current, I. They want us to find I1 and I2, okay? So Z1 is equal to 8 plus J6 ohms, and Z2 is equal to minus J6 ohms. So those are the two impedances. Let's see, and they tell us that I, current flowing from the source right here, voltage source, is equal to I is equal to 10 ohms, angle 0 degrees. Oh, so they're making this current phasor. In this problem, they're making that current phasor the reference. Does it have to be I? You can pick any value as the reference. But once you pick the reference, whatever angles you get is in reference to that, right? For the most part, we try to find a voltage, and whether it's a line to line or line to neutral voltage as the reference, and then everything else derived from there. But in this case, that's what they're telling us. All right. So how do we find I1 and I2 if they're giving us this and they're giving us the impedance? So we use current divider equation. So I1 is equal to I times Z2 divided by Z2 plus Z1. And then the other equation is I2 is equal to I, meaning this I, the current coming into the node, is equal to Z1 divided by Z2 plus Z1. So you guys probably did this on your circuit analysis. It's a very simple, just a current divider. So those are the equations. There's another way you can do it. You can say, oh, if I find this and I know this, I can find this because I know that this and this equals to that. So if I find I1, I can say that I2 is equal to I minus I1, right? So there's multiple ways that you can approach the problem. Well, let's do it this way. And by the way, if we were to write the answer the right way, but I won't hold you on that, but you circulate this. This should be a negative, and this should be a negative. And the reason being is because currents coming into a node are positive, currents leaving a node are negative. Does that make sense, everybody? Let's not worry about that. For now, let's just do it this way. So I'm gonna say that I wanted I1 is equal to 10 angle 0 degrees. That's my current coming into the node. That's the impedance. This is minus J6 ohms divided by 8 plus J6 minus J6, right? Everybody okay? So these two actually cancel. So what we get here is I1 is equal to, let me see. If I go through this, this is what I get. Minus, I'll give you all the entire process, but minus J 7.5 amps. As a matter of fact, I don't even have to do this minus. My apologies, because the angle is already going to give me that, right? I'll explain it right now. So I1 is equal to what do I get? 7.5 angle minus 90 degrees. Okay. So that's this current. Now, like I said, I can take this minus that, and I can find that. Or I can write it this way. Well, I'm going to do I2 is equal to I minus I1 base. So I2 is equal to 10 angle 0 minus 7.5 angle minus 90 degrees. If you plug this into your calculator, you should get I2 equal 12.5 angle of minus, oh no, minus, it's plus 36.87 degrees. And we'll talk about this in a second. But, or, as I said, you can use the long form. I2 is equal to I times Z, what did I do? The Z1, I'm sorry, Z1 or Z1. This is always the same, Z2, meaning the denominator is common, right? So I2 is equal to, sorry, 10 angle 0 degrees. That's how you write it. And in here, you can write it as 8 plus J6, right? That's Z1 divided by 8 plus J6 minus J6. This is always going to be the same. So my I2, again, same value I here. I2 is equal to 12.5 angle of 36.87 degrees. That's I2. Yeah. Okay. From here, let's see what was is that the final question? No, they're asking for voltage. We'll get there. But let's just take a look at this really quick. So they're telling me that there's three phasors that I'm dealing with right now. I have one here. Let me see. I have one here, right, which is I, which is equal to 10 angle 0 degrees. Then I have another one. Where's the first one? I got 7.5 minus 90. 7.5. Oops, I'm going to write I1. 7.5 minus 90 degrees. This is in amps. This is in amps. And then last but not least, I have another phasor going capacitor, which is this one right here, somewhere here. I'm going to say this is 36. I2, which is 12.5, 36.87. 36.87. And this is an amps. I have these three currents, and that's how they look. I mean, who plug these phasors? They haven't said anything to me about this voltage. although I know this current and I know this current, I should be able to find this voltage. Everybody agree with me on that? So, let's think about it. This current, just think about this current for a second, okay? This current is, this current right here in reference to this voltage, just reference to this voltage. I'm saying if I have a capacitor, okay, and I have it, let me see if I drew it here. I probably did. Hold on one second. Okay, yeah, I did. I thought I forgot. This current is the current going in through the capacitor, right? So if I had a voltage source, oh, I do have voltage. Of course, I can have a voltage source. Oh, so can you kind of guess where the voltage should be in this? Should it be in this plane, this plane, or that plane? Let's get this two out. Should it be here or here? Just before you do anything, let's look at the circuit. Take a look at the circuit. Just focus on the capacitor. What is a purely capacitive branch? There's nothing else. So that current should be doing what in reference to the voltage? Anybody? I know this is the current on the capacitor. And I know that's a purely capacitive circuit. So if I go by the rules that have been given to me, a capacitor current should do what? Lead by what? 90 degrees. So you'll expect the voltage, once we get a voltage, to land somewhere here, right? And be perpendicular to that. You agree with me, everybody? So the challenge is that here, they gave us not the challenge, but whoever brought this problem said, I'm going to pick the current as the reference. Okay, but based on the information I know, if I have these phasors right here, I know my answer for the voltage is going to come somewhere here. I even know the angle, but let's assume that we don't know the angle yet, right? So how do we find then the last thing is the voltage, right? I can use either this current times this current times this impedance, or this current times this impedance, and I should come up with the same value for this voltage and things are right. You know, if our theories, so I can say that V, oh, maybe this isn't good. V, sorry for that. Maybe this will be, and I'm talking, once again, I'm talking about the voltage that is driving the current through those impedances. So the voltage driving the loads. V is equal to I1 phasor times Z1, okay? So V is equal to I1 is 7.5 angle of minus 90 degrees, everybody okay with that? And the impedance Z1 is A plus J6, and this is in ohms, I'm sorry, and this is in amps. Those are the units I can put on. So voltage phasor is equal to 75 angle of minus 53.1 degrees. Oh, so the voltage is here, and I'm going to exaggerate it, but somewhere here. I happens to be 75, approximately minus 53.1 degrees. Oh, so that's this angle. So if I have this plus, and I'm going to take the absolute value, 53.1 plus 83.87, you should get close to what? 90 degrees, right? Yes.
I have a quick question. At least in my understanding, like the voltage seems to be leading the current here.
Okay, so let's stay with them for 1 second. Just that's yes, it seems that way.
Yeah.
It seems that way. But forget about this current for a second, forget about this current for just 1 second.
Yeah.
Okay, I want you to do this now. I want you to take this phasor and move it here. I want you to subtract minus 53.1. You see what I'm saying?
Yeah.
So basically, when I move this, remember when I said this is like bicycle spokes? If I have
Yeah.
the spoke right here and I move it, they all follow it, right? They all go together. So if I move this here to 0, this one, I'm gonna do it here, just those two. If I say, forget it, I want this to be my reference. That's the same thing as doing this, by the way. Remember I said this?
Yeah, but you would still have, your current still has a positive angle with that reference, so wouldn't it be lagging the voltage rather than leading it? A leading voltage has a negative angle with reference to the line, right?
No. I'm interested in the angle between them.
Okay,
I'm going to do it this way. Look, like this.
yeah,
Right? You see that?
yeah.
You see that? So the current is leading the voltage because that's the capacitor. Did I do this right?
I don't know why I'm thinking that the current should be facing down instead. It should be going down instead of up. That would be leading it, right?
No. Remember, if this is my voltage, you agree with me? This is my current. Is the current in front or behind the voltage?
Depends on how you look at it.
Huh?
Depends on how you look at it, right?
Remember, the voltage is always your reference.
Okay.
You always say, I'm gonna start from my voltage. I'm gonna say my voltage is there.
Going
If it's in front, it's leading. If it's behind, it's lagging, right? In this case, it's leading by 90 degrees, right? I'm gonna do it again. See this? Do you see this too? You agree this is I2. You agree this is V. If I go like this, you agree? This is still in front of it. Now, what about this one? You saw that, right?
Yeah.
Did I make my argument or not?
I think so. I think I'm just getting confused with the notation because if it's what I'm used to seeing is that if it's like negative J, for example, then the current is obviously facing down, and that would be leading whatever voltage you have along the x-axis, right?
I'm gonna say it again. How about this? How about you think of this? You spin,
Yeah.
right? This is gonna be spinning. And then you say, I'm going to wait for my voltage to come, right? And it's spinning, and then you see, boom, you see this, right? And this is gonna continue to spin, and what is the next one that is gonna come? This. Oh, I'm sorry, I'm gonna spin it. This is gonna come,
First, yeah.
and then right behind is that, right? So this is always is leading, right? Now, the reason why it might be confusing is because in this case, whoever put this problem said, I'm not gonna make the voltage the reference. I'm gonna make the current the reference,
Okay. Yeah.
right?
Yeah.
I'm making the current the reference. Oh, that kind of threw things off. But when we compare them, right, to among each other, regardless, this is always in front, leads. This is behind. Does it make sense that this is behind?
Yep.
Why? Because it's at the load.
It's inductive load.
It's an inductive resistive load. Is it minus 9? Is it 90 degrees in between them? No, because I have a resistance. If this was a purely inductive, then it would be like this. Then we'll have this. Something that looks like this. You agree with me?
Yeah. It'd be 180 degrees between both.
Like this,
Yeah.
right? It doesn't matter how I move it. Now, can I trick the system? Yeah, I can subtract 53, plus 53, but I got us plus 53 right here, right? It's the same thing, once again, as this. If you have a scope, and say in the scope, you say, no, I want this signal, whatever the signal is. Oh, let's call this signal B of t. I want to make this signal the reference. Okay? All you do is, you know how you move something and then you start moving this line until you get it to the peak, and this now becomes your reference. That's basically what we did. You subtracted or added the angle. Yes, sir.
So by virtue, V equal to I1 Z1, you will get the same thing as in V equal to I2 Z2.
Say that again. I'm so sorry.
No. I'm saying, like, instead of using I1 Z1 to find the voltage, you can also use I2 Z2.
Correct.
You still get the
I
same.
just think it's the same voltage. You guys can do it. right? Do it on your calculator. You should be able to get the same voltage. The other thing I want to show you is this. Let me see. Where's that? 0, 0. No, that's the only thing that I wanted to. Let me see. Yeah, let's leave it at that so I don't get overly confused. But the point I'm trying to make, so I got the voltage, right? You can try it. Can somebody do this for me? Can somebody do J 0 minus J times what is the other one? 12.5 times 36. Well, you should get the same value. Let me know if you don't, but you should. In other words, if I do this, this is what I'm saying. That's the voltage across those impedances. Or you can do it this way, you should get the same thing. I don't want to erase this. You can say V is also equal to I2, which is 12.5 angle of 36.87 degrees times minus J6, and that should give you the same thing, 75 angle approximately minus 53.1 degrees. Does it make sense? That's the piece that I want to make sure that you guys can see this, right? It doesn't matter. So you can pick any. As a matter of fact, I can rotate this in this direction and make this the reference, but these angles in between them remain. It is the angle between the phasors, not so much the angle that you're measuring. Does it make sense, everybody? Okay, I'm interested in the angle between those phasors. All right, so that should be the answer. I'll give you those solutions. I didn't do a really good job on.
Add some comments.
Say
And
it again.
the total current will be leading by 53.1.
The total current.
The 10 with a 0 degrees. If you reference in the voltage, the total current actually leading by 53.1 degrees. The green one.
By 90, no?
Yeah.
The green
Yeah.
one.
Yeah.
That's the total of with the inductor.
Remember, by the way, here's the other thing. These two are in parallel, they're not in series.
53.
Do I make sense, everybody? These are not in series, these are in parallel with each other. Do I make sense?
Yes.
This is not like I'm canceling them. Do you agree with me?
Yeah.
I'm not canceling them. Here, if the circuit looked like this, that's a whole different issue. Because now they're in series with each other. They cancel. So if the circuit was like this, sorry, I'm modifying it because that would. If this circuit was like this, everybody, what do you expect?
Purely resistive.
This is a purely resistive. So the voltage here and this current will be what? In phase with each other, right? But that's not the case. Well, be careful. These two guys are in parallel with each other, not in series with each other. Is there such a thing as cancel? Yeah, you can come up with the value that can cancel that in parallel. Okay, but that's not the case. All right. Any questions? I won't get this deep into this whole theory once you do it, but what I want to make sure is really that you get a grasp for the relationship between phasors. I don't want you to focus too much on the angle that you're measuring. I want you to focus on the angle between them, because the angle between them is what's telling you, right? So if you did all this, right? For instance, you ended up, the current flowing through this inductor in comparison to this voltage is lagging, then you know you did something wrong. Right?
Mhm.
In the test, say for instance, you come out at the end of the test and you put these phasors and you find out that this phasor, here's the voltage, Here's the current on the capacitor. Somehow you get a phasor somewhere here. When you're doing it, you have no more time. You're like, oh, it's 9:45. I gotta go. We gotta go. I'm getting this. If you tell me, hey, I got this answer, I don't know what I did wrong, but I'm expecting my phasor to be here, not here. And you tell me that, I'll give you a lot of credit for that. Because once again, we're not perfect. I'm not perfect. I make a lot of mistakes. You guys always catch me doing math mistakes. But when I land to the answer, does my answer make sense? That is way more important than the answer. Obviously not, right? But you want the right answer. What I'm saying is, it is the most important thing is, do you understand the relationship between these components? One type of branch versus voltage and current, how they relate to each other. And if there's anything that you don't feel comfortable, by the way, you can go do this on MATLAB and double check. Don't we have something like this in the lab? Even lab number one, we do three. Oh, it's
Yeah,
three
we
phase,
did.
right? We
Yes,
did it.
3-phase.
Yeah, so we did it by hand, like this. We did it
In MATLAB.
in MATLAB, and we did it
Simile.
also
Simile.
on Simile. I'm like, come up with very similar numbers. It would be nice to have a scope, by the way. I asked for a oscilloscope because I always wanted to show the time domain signals, but unfortunately they said I have to go borrow some probes and stuff, and they don't. I have to go get them. They return them. I have too much work. But if I did, it would be nice. If you ever have an opportunity to do that, do it. Just to prove yourself and be sure you're comfortable with this concepts. Okay, so that was that problem. Um, any questions? Everybody okay? All right. What was the next problem? That was it. So homework number 2. That was homework number 1, right? Or was that homework number 2? Anybody? Homework number 1 or homework number 2? Number 1, okay. So let's do homework number 2. Let me see. 2. Okay, here's the homework number 2. 2.7, 2.8, okay. Okay. Homework number 2. We're given the following circuit. We're given this voltage. Hold on one second. See if I can find a graph. All right, so let me just read it really quick. See what um, 2.19, 20, plus 3. Hold on, everybody. Let me just make sure that I'm 1 over 2. 2.5. 2.5, we're given a source with, yeah. So we're given this source, V is equal to 277 angle 30 degrees. Okay? So that's the voltage. And then they're asking us to find the time domain signal. Is that what it is? A 60 hertz single phase source volts applied to a circuit element. A, determine the instantaneous source voltage. Also determine the phasor. Okay, yeah. So the source voltage. So basically what we have is this. And we have a resistor. Again, V. And they're asking for I. Yeah. Actually, the question is, what's IRT? What is the instantaneous current for a purely resistive circuit with an impedance or resistance of 20 ohms? That's A. Is that what it's asking me, A? Or is that B? Hold on, my bad. No, the A is just to find the instantaneous voltage. So V of t then is equal to V max cosine omega t plus phi V. Okay? Oh, I know V RMS and I know angle phi V. Everybody okay with me? Let me see. This one's better. This one is better. Okay, so then I can say that V of t is equal to square root of 2 times 277 cosine omega t, and this is plus 30 degrees, okay? So this is A. So that should be equal to, that's it. 277 actually is V of t is equal to 480 cosine omega t plus 30. Can somebody do this for me? I'm pretty sure that's what it is, but meaning 277 times square root of 2 should be 480. All right, so the next question is, oh, can you find the current if this is a purely resistive circuit? So that's B. So IR is what they're asking me. IR. So, therefore, IR is equal to V, which we already got, phasor divided by R. That's equal to, 277 angle 30 degrees divided by 20, right? Ohms. This is volts. Then IR phasor is equal to 13.85 angle of 30 degrees, okay? Let's enter it this way, 20 angle 0, and this is in ohms, right? If you were to enter in Polar form, 277 divided, angle 30 divided by 20 angle 0 gives me that which is in amps. Does it make sense? Of course, it makes sense, right? Because that's the resistive circuit, the voltage and the current are in phase. Let's be C. See, they're saying, oh, what if you have the same voltage source, but instead you have an inductor right here. This is V, which we already know what it is. And this is a inductor, L equals to 10 millihenries. That's what they're telling us this is. And they want us to find the current phasor and the time domain. So we want IL of t and IL. So in the phasor and the time domain of this current right here, I want to say this is IL. Okay, oh, we have an inductor here. So remember, when you have an inductor, you got to convert that to make it easy. You got to convert that to a reactive impedance, so reactive inductance. So that is equal, and they tell us, by the way, at the beginning of front, this is 60 hertz, and it's always going to be 60 hertz unless you go to Europe, but we're not there, so we're going to use 60 hertz. So we know that JXL is equal to J omega L. This will be in ohms. So JXL is equal to J377 times 10 to the minus 3. 377 times 10 times 10 to the minus 3 because it's milli, so I said I wanted this to be in Henry. So this is in Henry, this is in radians per second, right? So if you do this, JXL is equal to J 3.77 ohms. Okay, so now I can draw the circuit in the phasor domain. Okay, this is once again 277 angle 30 degrees. That's 30. Yeah, this does not change. This is my voltage source, my current IL, and this is I'm sorry, 3.77 ohms. Therefore, my IL is equal to V divided by JXL. So IL is equal to um, 277 angle 30 degrees divided by J 3.77 ohms, and this is in volts, or you can write it 0, or you can write it 3.77 angle 90 degrees, whichever way, polar, rectangular, it doesn't matter how you want to write it or enter your calculator. So if I do that, then I get 90 degrees, I get IL phasor is equal to 73.47 angle of minus 60 degrees. Minus 60 degrees. So this is a purely inductive circuit. Um, so, does it make sense, everybody? Am I getting the right angle between the voltage and the current? It's exactly what I was saying in the last problem. Here's my voltage. I'm going to say this is 30 degrees. Okay? Here's my current. That's 25. Here's my current. This angle right here is minus 60 degrees. Okay? That's I, that's V. Remember, I'm going to say it again. Who cares about the voltage from the x-axis? It's the voltage between the two of them. 30 plus 60 is equal to 90. Does it make sense? The current is the what? Lagging the voltage. Is behind. If I turn this, I is going to come, I'm sorry, V is going to come, then I is going to come after that, right? So the current is lagging. Yeah, makes sense. This is in amps. Now they said to me, oh, can you give me that information? Not only as a phasor, but I want to know what the answer is in the time domain. Well, here's my V, R, and S, and here's my P, I, L, I'm going to call it. Oh, then I can say IL of T is equal to square root of 2 times VRMS, oh, IRMS, I'm sorry, 73.47, and, oops, I'm sorry, cosine omega t minus 60 degrees. Everybody agree with me? So this right here, if you give me this on a test like that, that's it. That's the right answer. I mean, you can do this if you want. You can take square root of 2 times that and give me just a single value. So, or whatever it is. I didn't do it. You know what I'm talking about, though, right? If you do in your calculator square root of 2 times 3.47 and put that value in there, or you can leave it there and it's still right. Any questions about that one? Everybody okay? All right. The last one is they're saying, okay, what if now you have the same circuit, but instead you replace the impedance by a capacitor. So V again, here's my source, here's my capacitor, and the problem, let me see what the problem says. The problem says, oh, do you see how on D, it says, if you read the problem on the book, it says, oh yeah, what about a capacitor of 25 ohms? They're not telling me, they're just saying 25 ohms. I know, because of what we have discussed, that I know, we know, that 25 means what?
Okay.
It is it's an imaginary value, it's a capacitor. And in addition, it has to be negative because it is a capacitor, it's not an inductor. So, the book says 25, and that's trying to trick you on that. So basically, this is minus J to 5 ohms. And we can find this current, IC, and we know the voltage, so we know that IC is equal to the voltage divided by the impedance, which is JXC. And by the way, sometimes they don't have to put a minus, they call it JXC, okay? We know that this is, once again, 277 angle 30 degrees divided by, you can write it this way if you want, 0 minus J 25, right? If you want to write it as a rectangular number, it's in ohms. Or you can write it 25 angle minus 90 degrees if you want to write it in polar form. So IC is equal to, I get 11.08 angle of 120 degrees. So does it make sense? Yeah, because if you look at the 30 degrees, right, the voltage, the current in this case is leading, is the angle in between. Remember, you have V30. This one is 120. I'm interested in the angle between them. So 120 minus 30 is plus 90, therefore leading. I know it's a capacitor, so that answer makes sense to me, or to us. Now, C of t is equal to I max cosine omega t plus phi I, okay? This is I RMS, I max is I RMS times square root of 2, right? So that one, the time domain signal for the current should be I C of t is equal to square root of 2 times 11.08 cosine omega t, right? Plus 120 degrees, and this is also enough. So those are the answers. And then last but not least, oh no, that was it. Then the next one, any questions about those? Those are very simple problems. You should be able to go through them fairly easy. The next one, they said, let a 100 volt sinusoid source be connected to a series combination of resistor, inductor, and a capacitor. You see how that problem, that's what they give you? They don't tell you which one's real, which one's imaginary. Just give you three numbers on that problem. So basically what they say on that one is, hey, I have a circuit that has three components in series, and they're driven by a voltage source. That's 2.7A. What I have is this. I have a resistor, I have an inductor, and I have a capacitor. And I have a voltage source, and what they tell us is the voltage source is equal to 100 angle 0 degrees. Oh boy, they made it simple for us. In this case, the voltage is the reference, so that's going to be, that's simple, right? So they're telling me that this is 3 ohms. They're telling me that this is 8 ohms, so this is J8 ohms. And they're telling me that the capacitor is 4 ohms, so it's minus J4 ohms. And this is Z. And what they want us to find on the first one is the impedance of that circuit. So, really quick, is this a inductive resistive or an inductive capacitive? I mean, a resistive inductive or resistive capacitive circuit?
Resistor inductive.
Yes, resistive inductive, because once you Once you add the imaginaries, you're gonna end up with a positive value, which is telling this is our L circuit, even though you have a. But they're in series. Remember, again, this is different from this. Everybody, this is not the same as this. Just want to make sure you don't get confused on that. All right. So A was just to find Z. So Z is equal to R plus JXL plus JXC. Z is equal to A plus JA minus J4. So Z is equal to A plus J4 ohms. Everybody agree with me? Right? That was very simple. Nothing overly complicated. So let's see. Ooh, that's the first one. The next question is to find the current, this current, I, driven by this voltage to the, or drawn by this impedance, I'm sorry. So we can say then, we can, if you want to, you can draw it this way. Now, if you want, you don't have to. And this is 8 ohms, and this is J4 ohms, right? And here's my I, and here's my V. Okay, so now I know that I is equal phasor, the voltage simple divided by the impedance, Z, or I is equal to 100 angle 0 degrees divided by why did I do it this way? Hold on, everybody. Oh, nobody caught me on that one. This is 3. Yes,
Professor, the bottom ones are wrong too.
The bottom one is wrong.
Your answer, you put it.
This is wrong. This is wrong, right? That should be 3. That should be 3, correct? Thank you, everybody. My bad. All right. So, again, 3 plus J4 on my current. So I know one thing right now. I know the voltage is here. V is equal to 100 angle 0. Once I get the answer, if I did everything right in my calculator, is my current going to be here, here, or in between, or in between? Where should my current be? Here's my voltage. My current should be somewhere here, right? Lagging, not 90, because I have a resistance, right? But somewhere in between. Okay, so if I plug that into the calculator, I is equal to 20 amps angle minus 53. I get 53 degrees, and calculator might get 53 point something, but approximately that, right? Does it make sense? Yeah. My current is right here, and there is minus 53 degrees. And the current is lagging the voltage. Yes, it's an inductor resistance circuit, right? Okay. What about the power factor? The power factor is equal to the angle between the voltage or the current, or theta. I say this is the best way for you to approach this kind of problems, right? Than guessing, or not guessing, but than just grabbing the angle by looking at the phasors. It's better to do it this way. You is more comfortable if you say theta is equal to phi, always voltage minus phi I. And the reason being, once again, is because if I had shifted this voltage by 10 degrees, right, things will be shifted by 10 degrees. I mean, currents will be shifted. So the best way to get theta is just, I'm looking for the angle in between. So use this formula, which we know where it's going to be in this case, right? We know it's going to be theta. What is the angle of the voltage, everyone? Zero. Minus, what is the angle of the current?
53.
Minus 53. So I know that theta is equal to 53 degrees. Everybody agree with me?
Yes.
As I said, if I've shifted this by 10 degrees, then this will be 10 degrees, this will be minus 63 degrees, right? But when I do this, I'm always going to come up with the angle between the voltage and the current. So the power factor, we know the power factor is equal to cosine theta, the phase angle, which is cosine of 53. So power factor is equal to 0.6 power factor. Am I done? I'm missing one thing. Leading or lagging. This is a what kind of circuit? Inductive resistor. So this gotta be lagging. Now we know that because from the phasor, right? Lagging. Okay. Is this a good power factor or is that a bad power factor, everybody? That's a little poor, right?
Can you repeat the top part when you shift 10 degree and what?
Oh, I said, okay, what if I shift all of this by 10 degrees? Meaning if I shift the voltage by 10 degrees, I gotta increase it by 10 degrees.
So 43.
So if I have the voltage, I have this, right? So I have this, and I have this. I'm moving both of them by the same degree. And that's what I said. The formula is important to write it sometimes because that will make sure that you keep the angle between these two phasors.
So we will never have to worry about anything. Just do that formula and
That's the formula. I mean, eventually you see it, right? After you do it over and over again, you know what you're after.
Professor,
Yes.
what determines like a good power factor for like a bad one? Because 0.6 seems pretty close to like 1. Why wouldn't that be considered?
So remember that the power factor goes from the maximum you can have is what, everybody?
1.
Unity, right? Cannot be greater than that. And then you go down to say 0, but not gonna say 0. So this one is telling me that whatever system of load I have, say the load looks like this, right? And say the power factor is 1. That means that I have a capacitor here. And I see the power factor seen from the source, right? If it's 1, that's telling me that the bars that are consumed by this inductor are produced by this capacitor, right? So the source, the utility, is only selling me what?
Yes.
P, real power, because my reactive power Q is handled internally, right? That's a really good power factor for the utility, right? And I said it before, say this is an induction motor. Say this is an induction motor. Your induction motor is not going to change unless you rewire it and you redesign it, right, to improve its power factor. But no, you're not going to do that. So if you don't have a capacitor, the utility say that the induction motor has a power factor of 0.6 lagging, right? The utility says, oh, I got to provide you with the real and the Q's to run that machine, okay? 0.6, but that's very poor power factor. And then you say, and you know what? I'm gonna go to the extreme. I don't wanna draw any Q from the utility, but the motor still drawing the Q. You cannot get away with that, right? So you're gonna put a capacitor here that produces the same amount of bars that this consumes. So now to the utility, it's a unity power factor. You're only selling that, right? Better yet, how about if I put a capacitor right here to bring the power factor to 0.8 or 0.85 or 0.9 or 0.95, right? anything above 0.8, I'm gonna consider that a fairly good power factor. Anything below the 0.8, you know, because what that is telling you is that is the amount of bars that the utility is having to produce to manage this load. Make sense?
Yeah.
Okay, so that's that. So, I mean, this can be the follow-up to that problem, right? Follow-up could be like, can you improve the power factor from 0.6 to 0.95? All you do is you take the cosine, the inverse cosine of the new power factor, you find the angle, now you find the new, with that you find a new Q, with that new Q you subtract it from the source, and that's your capacitor, right? You guys know how to do that. All right, so that was it. Let's see, 8:47. We still have time. Just want to make sure that 2.8. How about if I do this? 2.8. We did this already. I might come back to 2.8, but how about if we do that just in case we run out of time? I'm gonna do the other homework. And that's what I was telling you guys, I couldn't convert it, so I have it on my iPad. But I'll give you the solution. So homework number 3. Oh, bless you. Homework number 3, they make me 3. This one, as I said, I'll give you all this info, you guys don't have to worry about that. Do I have it here? Homework number 3. Is it problem 219 on homework 3? Anybody?
Yes.
19, 20, and 21, I think it is.
Yes.
Right? Thank you. All right. So let's do that one just in case. I think the other one, 2.8, is very similar, and I'll give you the answer. As long as you know how to do this, you should be okay. Trust me, the exam is going to be a lot easier than this. If you know how to do this, you're good. You're in good shape. All right. For the next one, we're given, let me open it just in case. Homework 3. Sorry, everybody. I put them towards the end. Sorry, here it is. So it says a single phase. Was it a single phase or 3 phases? 19 says, consider a single phase load with an applied voltage of V of t and a current on the load of blah. Determine the power triangle. Find the power factor, specify where it's leading or lagging, and calculate the reactive power. Oh yeah, there is a power factor correction. All right, so this is what they're telling us. You have a circuit, and I don't know what the circuit is. All I know is this. I know this voltage, and by the way, I know this current. I don't know what this is. But what they're asking me is, can I find the real reactive and apparent power drawn by this load with the given information? V of t is equal to 150 square root of 2 cosine omega t plus 10 degrees, and then I of t is equal to 5 square root of 2 cosine omega t minus 50, omega t minus 50. Okay, so that's my voltage in the time domain, and that is my current in the time domain. I don't know what kind of load it is, but I can actually take an educated guess just by looking at the angles between the voltage and the current. Oh, this is minus 9. Oh, that signal is behind that. Who cares? It's just behind. Not 90 degrees, somewhere in between. So I know, they haven't told us the resistor, but I know just by looking at this phase, at these two signals, that this is a
Inductor.
resistive inductive circuit, right? So let's find the phase circuit. 150 times square root of 2 divided by square root of 2 angle of
10 degrees. So V is equal to 150, cancel that, right? Angle of 10 degrees, that's my voltage. My current is equal to 5 times square root of 2 divided by square root of 2, angle of minus 50 degrees. So I know that I, phasor, cancel, is equal to 5 angle of minus 50 degrees. Okay, so now I know V and I know I. And I know this is single phase circuit, so I don't have to worry about 3s and square root of 3s, right? Everybody? Unless it was a three phase, then all bets are off. I gotta use a different formula. I gotta think about voltages line to lines, line to neutral. But in this case, that's not nothing that I should worry about. You can say, okay, how about if I theta? In case I need it, which I will need it. I'm gonna say theta is PV minus VI. So theta, or the phase angle for the circuit, is equal to 10 minus 50. So theta is equal to 60 degrees, right? I know theta in case I need it, and I know the two phasors, V and I. Then I can say that there's two ways actually to do this problem. Let me see. You can, one way could be that you write this equation. S is equal to V phasor times I phasor conjugate, right? That's one way. Don't forget that this is the conjugate. Or we'll do it the long way. Either way is fine. We can say P is equal to V magnitude I magnitude cosine theta. So in this case, we say that P is equal to, remember, this is RMS, this is the magnitudes of the phasors. So 150 times 5 cosine 60 degrees. P gives me, if I do that, it's about 375 watts. Okay? Q, I can put J. JQ is equal to J V magnitude I magnitude again sine of theta. So JQ is equal to J 150 times 5 sine of 60 degrees. So JQ is equal to 649 bars. Sorry, bars positive. Bless you. Look at this. Just by looking at the P and the Q, actually let me do this before I go there. S is equal to magnitude. P squared plus Q squared. So S magnitude is equal to 375 squared. 375 squared plus 649, 650, 649 squared. S magnitude is equal to about 750 approximately volt amperes. Okay, that's just the magnitude. Let's see. Okay, so basically I have a transformer that is full capacity is 750 volt amperes. And the way I'm splitting my real and reactive power, I'm saying, oh, the real power is somewhere around here, and the reactive power is this. This is 649. This is 375. Right, just by looking at the values, the magnitudes, do you think this transformer is being used very efficiently? Not really. It has a very poor power factor, right? Because it has a lot more reactive than real power. So that I know. Just by looking at the values, I know that whatever I'm doing here is
This is not very ideal case on how I want to run this transformer. I'm going to call it transformer, and we'll talk about it in a second, why I'm calling it a transformer. So the power triangle for this is that, right? P is equal to 375, W, JQ is equal to 649 VA, bars, and then this magnitude S is equal to 750 magnitude VA, or volt amperes. What is this angle, everybody? What is the angle? Do you see an angle anywhere that you might want to use?
60.
60, right? 60. 60 degrees, that's the angle. So the power factor, P, power factor is cosine of 60 degrees, lagging. So the power factor for this is equal to 0.5 lagging. This is not good. Should be very poor power factor. The question is, how can I improve this to, how can I improve, or what do I need in order to get the power factor to be a little better? And a little better, they're asking us for a power factor of 0.9. Improve this to 0.9 lagging. All right, so what do we need to do? Well, we need to find an angle nu, theta nu, is equal to the cosine inverse of the power factor. So theta nu is equal to the cosine inverse of 0.9, and that gives us theta nu is equal to 25.84, 25.84. Basically, what this is telling us is this. Here's 60 degrees, and they're asking me, well, I want you to include the power factor 0.9, and if I go through that exercise, all I'm doing is I'm reducing the angle. I'm reducing the angle here is resulting into reducing this magnitude, right? Not this, I'm not touching the real power. What I've been asked is to bring this down. And if I decrease the angle, of course, that's what I'm doing. I'm bringing the reactive power down. All right, so with that, I can say that Q is or source. I'm saying, hey, how the utility sees this transformer bank right here is a 0.5 power factor. So this, in order for me to improve the power factor, the source is not going to give me all that reactive power, but it should give me something less. So how much less? Well, the formula is P, that doesn't change, tangent of theta N, which is the new angle. So the Q source, I'm going to put a J so we know it's a J. Source, you guys know it's a source, is equal to 375 times the tangent of the new angle, which is 25.84, and that gives me JQS of 181.62 bars. Oh, so what you're telling me is I'm going to improve the power factor from 0.5 to 0.9. What that is going to result is going to result in me, utility, only giving you 181 bars. You, inside whatever substation, got to provide me with something, some sort of bars, so that I can only give you. You give me the rest. All right. So if that's the case, then I'm going to move right here, everybody. I'm going to move right here. So the capacitor then, the JQ cap is equal to the JQ total of the load, right? That's the load. The load connected to this transformer, whatever load it is pushing that much power minus JQ source. Oh, this is what I'm getting, what the source of the utility is gonna give me. So I gotta provide this. So JQ cap is equal, the load doesn't change. The load is going to remain 649 649 minus 181.62, which is what the source can only give me, so the cap needs to be this big. The cap is equal to 467.8 bars. The way you can think of is this. This is a substation. Here's my transformer. My transformer is pulling, I'm gonna say, total of 649 VARs. Okay? Inside the substation, I'm going to put a capacitor that gives me 647 VARs approximately, so that the utility of the source
You mean 467?
only gives me,
467.
oh, I'm sorry, thank you.
You have a power factor of
467, right? So basically what I'm saying is, oh, okay, so the utility, the generators on my system are only have to provide me with 181. The transformer is drawing 649, but I'm gonna give it inside the substation by putting capacitors 667
467.
467, I'm sorry, keep on saying that. 467 of the 649. So I'm improving my power factor. The transformer still does it. The transformer doesn't care. It is what it is. If it's a motor, it is what it is. It's what I put in. So improve power factor. This one right here is the one that I told you guys that if you want to just take any of those problems that I have given to you and they just put step 1, 2, and 3 so that you don't get confused and you don't forget. First, I find my P and Qs. Once I find my P and Qs, I use the new power factor. With the new power factor, I find the new angle. With the new angle, I find the Q of the source. The Q of the source, then the load and the load minus the source gives me the cap. I'm not gonna ask that to be in Henry's. Paris. Don't worry about it. Okay, any question? So that's a good homework. That's a good problem for the exam. How much time do I have? I don't have a lot of time. All right. Let's see. Let me jump to this problem because the other ones are a little similar. A little. I just don't want to run out of time. And I'll give you the answers. So don't worry about it. You will have all the answers so you can review your work. I'm going to do this one. And if I give you anything like this on the test, it will not be as complicated, by the way. So, I'm going to do something a lot more simple. If I, not saying I would. This is homework number 4. Homework number 4 says, problem number 1, a balance. One second. Okay. All right. So a balance delta connected impedance. I'm not writing exactly how it's in the exam, but it's the same thing. Impedance on the homework problem, and it has a Z delta of 12 plus J9 ohms, okay, is connected to a source of a balanced, well, we know it's three-phase because it's delta connected, right? To a source three-phase 60 hertz of 208 volts. And then the question is, A, find the line current, total P, Q, and S, and the power factor. And then B, they're asking us to draw the phasor diagram for line currents, load currents. Actually, the problem only asking for line currents, I think I'm load currents, but I'm gonna do all of them so that we know how to do all of them. Phase-to-phase voltages, phase-to-phase voltages, and phase to neutral. So I'm gonna do them all. Okay. As I said, I think the homework only asks you for two of this. We'll do the whole thing. All right. So if you have a problem like this, the best thing to do is just to draw the one-line diagram for yourself. So that way you know what they're asking you for. So they have this load, which is a delta connected to this Y. Actually, this. I'm going to call this V, A, V, B, and B, C. And they have a neutral point right here, N. I'm going to call this Z delta, Z delta, Z delta. So it's a balanced system, meaning this impedance are the same. These voltages have the same magnitude, 120 degrees from each other. In the problem, they tell you, hey, use the AP voltage or the line-to-line voltage as the reference. That's what they tell you in that problem. So basically, why is it that? So the voltage 208 that I gave you, what kind of voltage is that? Three-phase, is it line-to-line, is it line-to-neutral?
Line-to-line.
Line-to-line. The problem here doesn't tell you, but we know it's line-to-line because it's a three-phase source. So that's a line-to-line. And in addition to that, they're telling me, hey, not only is line-to-line, make that the reference. Make that voltage AB reference. Okay, so you can do that. You can write it down if you want. AB is equal to 208 angle of 0 degrees, and this is in volts. In other words, I'm going to start from that point. Okay, we'll talk about the other voltages. Now, the next thing is they tell you, oh, here's the impedance. What was it? 12 plus J9 ohms. Oh, this problem is not that friendly because my load and my source are not connected as Y. So if I want to take one phase and do the analysis on one phase, I cannot do it. And by the way, let me just label this. This is voltage line to line. This voltage is line to neutral, if you want to label them. Well, what I gotta do is I gotta make some changes to this. So the first thing you wanna do is when you have a delta, you wanna convert that to an equivalent y. By the way, the equivalent y that you come up with is going to draw the same amount of power, whether it's delta or y, right? But in this case, we're gonna come, how do we get an equivalent of that? So the zy is equal to z always, z delta divided by 3, okay? So zy is equal to, again, 12 plus j9 ohms divided by 3. So zy is equal to 4 plus j3. Everybody agree with me? I just divide this by 3. So my circuit now, now it looks a lot better, a lot more friendlier, so that I can do my analysis on the per phase basis, because my impedance then looks like this now. Remember, the amount of power that the delta and the y consume is the same, okay? So if I do this, then I have this neutral right here. I'm gonna call this VA. I'm gonna call this IA. So that's my line current. The current flowing on this wire is the line current. The line current, the current flowing on this wire, I'm gonna call this IAB, is the load current. Make sense? The current flowing on this wire, I'm gonna use a different color. The current flowing on this wire right here is what I call the I line. In our case, I line. This is equal to IA coming from source A. The current flowing here is the I load. This is the load. This is the load. So the current flowing here is I load. Make sense, everybody? This is the line. This is the wire that I'm using to connect this load. Inside the load, these are the loads. The current flowing here is the I load. This is the I line. So when they tell us I line is what is on that wire. Okay, so now that I have the circuit right here, I can say this is V, B, C. So I have IA, IB, and IC, and this is my I neutral, which in my case, because this is balanced, and if I add those three phases, what do I get? If the system is balanced, same magnitude, 0, right? I should get 0. But this is ZY now, which is equal to, what's it, 4 plus J3 ohms? Okay, so I can pull that circuit, right? I can actually use this and take this right here and make it just one phase. Treat it as a one phase circuit. So I can then do this. I can say that, let's see. All right, so what about my V? So I know VAB is equal to 208 angle of 0 degrees. That I know, right? I know this phasor, VAB. What do I know? If you, this one's the one that I was telling you that I want you to go to the slides or that I gave you. You can do your deltas and y's if you want. If you want to take a little picture and make a copy of it and then paste it, I'm okay with that as well. But I'm gonna go this way. So I'm gonna say, oh, I know that the voltage, I know the voltage between the two wires. I want to know what the voltage is between that one wire, one of the wires, and the neutral point. So that is equal to VA to neutral. And VA to neutral, oh, okay, so that is 208 divided by square root of 3 angle of, so we know that the we know that if I have the AB voltage here, if you go to my notes and the slides, you don't have to, because it's always gonna be like that. You're always gonna follow that. I know that if I use my AB as the reference, the magnitude of A to neutral is going to be smaller by the square root of 3, but there's going to be a 30-degree shift. It's going to be behind right here. So this is minus 30 degrees. We don't come out with that for magic. I mean, I did the math for you guys on the slides. You just got to remember that, well, not remember that, but put it on your cheat sheet. Okay, but if you follow it, that's what I show you. So VA to neutral then is equal to 120 volts angle of minus 30 degrees, and this is in volts. That is really the transformer. We'll talk about transformer next week. There's something we're going to talk about this week. That is what you're getting out of your transformer on the pole. Between the two wires on the transformer, your pole is 208 volts. Between one wire and the center point is 120 volts. Okay? So, and we'll talk that, like I said, when we talk about transformers, we'll go back. But the point I'm trying to make is that if I make this AB 0, the angle right here is always gonna be minus 30 degrees. The line to neutral voltage is gonna be behind. So if this was 60, minus 30. If this was 10, minus 30 is the angle in between, right? That's what I'm interested on. Okay. Look my notes, the slides, and follow this problem. So, now I have this circuit. Ooh, I know the voltage. I know the impedance. I know that the voltage here is equal to 120 angle minus 30 degrees, assuming, once again, that I use this as my reference. On my current IA, for the line that is going to flow through this wire, is going to be whatever that divided by the impedance, which it happens to be 4 plus J3 ohms. So IA phasor, or the line current, is equal to 120 angle minus 30 degrees volts divided by 4 plus J3 ohms, and then IA is equal to 24 amps, 24 point something. If you do it on your calculator, I'll write it to 24. 24 amps at minus 66.9 degrees. That's what I get, amps. Oh, so you're telling me that you now know this current, the line current. Yep, I know, I'm sorry, this one. I know IA. I know IA. I know this voltage, V, A to B, and I know the voltage A to neutral. Ooh, I have three things now. We'll come back to that. Okay, so if we go back to this one. So you said, oh, I know this current. I use this method. I converted the delta to a Y to find an easy way to get this current. When this current, look, just follow it. It gets to this point, it's gonna split. Okay? So the current that goes into the load, don't worry about the angle yet. We'll talk about the angle in a second. But the current that is gonna split, coming in from the line, and it's gonna split because it's a delta, it's gonna go in two directions, either this direction and this direction, but it's going to split. Is the magnitude of that current going into the load gonna be larger than the line or lower than the line?
It's a lower, no?
Again, I'm coming. I'm gonna use the word split for a second. Forget a direction, magnitude-wise. I'm going here, boom, I get to this point. Current is gonna go in both two directions, right? Is the current magnitude here on the line larger than this two or smaller than this two?
It's larger.
This has to be smaller, right?
Yeah.
Because it's splitting. Magnitude-wise, splitting by what, everybody? Square root of
Three.
3. I gave you those pages, but it's the square root of 3, so you don't even have to, you just say, oh, okay, so how do I get, oh, by the way, I have an angle here, and that's my reference in comparison when I'm comparing the currents. So I know this now. What I know, again, you have to go to my slides. I'm gonna say, I know this current, I A, I know that current IA, and I know this current is about, magnitude is about 24. Oh, I know the angle, minus 66 approximately, right? The current on the, as a split, right? The current is going to be smaller. And what is the angle in between them, everybody? IA is going to be 24 divided by square root of 3. And what do you think the angle between the phase, the line, and the load currents are? What angle are we talking about? We're talking about how many degrees?
30.
30 degrees. 30 degrees. And as I said, go to my slides, and in the slides that I explained this to you guys, and I said, oh, this guy is gonna be ahead. Ahead. Always. If I have this is gonna be hit by 30 degrees, so there's 30 degrees between this. That's what I'm trying to say. So if that is the case, then I can write the IAB, or the current going through this load, or through this load, or through this load. And that's going to be 24 divided by square root of 3. Angle right here is going to be minus 66 point, what I have, 0.9 plus 30 degrees, because it's ahead, right? Okay, so IAB is equal to 13.6 approximately, angle of minus 36.9 degrees. 36.9 degrees. Oh, okay, so I have everything that I needed. I got my phase, my A to B voltage that was given to me, my A to neutral voltage that I just derived. I got my line current A, and I got my AB current. All right, so if I, so the next question was, oh, now that you know all the voltages and the currents, can you find the real reactive and apparent power and the power factor? Yeah, because I know the loads, I know the currents, I know the voltages. This is what I want you to be careful. I will not give you a problem with this because it's too long. But I could give you voltages and make it a reference and ask you what the other ones are. But so that you know how to do this, I say, okay, so I have enough information to write this equation. A3 phase is equal to, I'm gonna use that little circuit that I had with just the one phase, but it's aligned to neutral voltage, so I'm gonna use 3 times V A to neutral. This is line to neutral, that's what I use 3. This was AB, this is square root of 3, times I A conjugate. I have all that information. Okay, so my S3 phase, I'm going to put a line here so we know it's not just a magnitude, is equal to 3 times A to neutral is 120 angle of, what's it, 30, minus 30 degrees, I'm sorry. Minus 30 degrees times IA was 24 approximately, minus 66.9 degrees, 66.9 degrees conjugate. If I rewrite it, I 3 phase is equal to 3 times 120 minus 30. What is the conjugate of that? 24 angle of, anybody?
66.
66.9, right? Because I have it here, the conjugate is here, it's just the positive angle. So S3 is equal to, if you plug that into your calculator, you get about this, 86.54 angle of 36.89, 36.87, I'm sorry, degrees. And this is in volt amperes. Okay, that is in volt amperes. So there's a couple of things that I can get just from here, right? And then you can put them on the side if you want. I know S magnitude or the apparent power. That's 8654. 8654 volt amperes. I know theta. Don't we know the angle between the voltage and the current? 36.87. Everybody okay?
Yeah.
36.87 degrees. Okay, I'm going to put them there. I'm going to set them on the side. Well, this one isn't, they're asking me for that, but I'm going to set this one aside. You can convert this. You can make it as simple as that, right? You can convert that to what? You can make that, convert that polar from polar form to rectangular form, and that's what do you get out of that? P and Q, right? Or you can say 86/4 cosine 36.87 plus J 86/4 sine of 36.87, get the same thing. But because you guys want to do it quick, all you just plug it into your calculator and you get S three phase is equal to 69.23 plus J 51.92. This whole thing, the whole thing is volt amperes. But now I know P and now I know JQ, right? P is 69.23 watts. Q is J 51.92 bars. Everybody agree with me? So I know the real power, I know the reactive power, I know the apparent power magnitude, okay? All I need now is the power factor. That's the last thing that they're asking me. I'm not gonna erase this because I wanna come back to it. All right, so the power factor for this is power factor is equal to the cosine between the angle, I'm sorry, the cosine between
Of the
cosine
angle.
of the angle between the voltage and the
Correct.
current, theta, right? So that, in our case, we already know it. We place it over there, theta. So it's the cosine of 80, oh, I'm sorry,
36.
36.87. 36.87. I'm tired, but almost there. Power factor is equal to, I get a 0.8 lagging. That's not bad, right? That's pretty good. That's pretty decent power factor. It makes sense. I mean, from the real and reactive power, we always be drawing more real power than reactive powers. That's a pretty decent power factor. The last thing they tell us is to draw the spacers. I think they just tell you 3 of them. I'm going to do all 6 of them because now we have this information. VAB is equal to 208 angle 0 degrees. VA to neutral, we said that it was a 120 angle of, was it minus 30 degrees, right? IA was equal to 24 angle of minus 66.9 minus 66.9 degrees, and IAB, we said that was 13.8, I'm sorry, angle of minus 36.9 degrees, and this is in amps, this is in amps, this is in volts, and this is in volts. Phase to phase or line to line voltage, line to neutral voltage, line and load current. Line current, load current. All right, so if I want to know now if somebody's asking me for all, how many? 12 phasers, right? 12 phasers. I can start with the AB, VAB, VBC, VCA. Always in this order, everybody. A to B, B to C, C to A. Okay, always. Equal, equal, equal. But what I'm trying to say, B to A is not the same as A to B. B to C is not the same as C to B. And C to A is not the same as A to C. But we always go in that rotation, A to B, B to C, C to A. If you want to write it on your cheat sheet, I'm okay with that. So 208 angle of 0 degrees. That's my first one. I know that one. 208, the magnitude doesn't change. 0 degrees minus 120. Everybody agree with me? So this one becomes 208 angle of minus 120 degrees. 208, that doesn't change, angle of 0 plus 120 degrees if I'm going in the positive sequence rotation. So that's 208 angle of 120 degrees. And this is in volts, this is in volts, and this is in volts. So I have my three phasers. B to A, B to C, and C to A. Okay? Simple, right? Now, what about the line to neutral voltage? Well, I know the A to neutral. If I know the A to neutral, I know the B to neutral and C to neutral using the same approach. So I'm going to say V A to neutral is equal to 120, right?
Yeah.
Angle of minus 30 degrees. I'm going to keep that one. That's my phase angle. Oh, my volt V. So B to neutral, A, B, C. Positive sequence. 120 angle minus 30 degrees minus 120. So B to neutral is equal to 120 angle of minus 150, right? And the last one, V, zero neutral, 120 magnitude remains the same. I still have the phase angle, the V angle, which is 30 degrees, but I'm shifting it by 120 degrees. So V C to neutral is equal to 120 angle of 90 degrees. So now I have A, B, and C. Everybody okay with me? All right. Now, the next one, let's take the line current IA. IA is equal to 24 amps at an angle of minus 66.9 degrees, 66.9 degrees. And this, of course, is in amps. Oh, by the way, I didn't put the units, my bad. Volts, volts, and volts. All right, so same thing, IB. So what's flowing on conductor B? Well, conductor B has the same magnitude as far as current is concerned. And this is minus 66.9. This is phi A, right? That angle minus 120 degrees always because the rotation is IA, IB, and IC. So IB is equal to 24 angle of, where do I get it? Minus 186.9. Minus 100, oh, it's right there, 186.9 degrees. And this is in amps. And then last but not least, IC phasor is equal to same magnitude, 124 degrees. And now it is minus 66.9 plus 120 degrees, so my IC current then is equal to 24 amps, angle of 53.1 degrees. Okay, so I have my IA phasor, IB phasor, and last but not least, IC phasor. And last one here. Last one. The last one was IAB, right? So I have IAB, again followed by IBC, followed by ICA. In that order. IAB was 13.8, angle of minus 36.9 degrees. Minus 36.9 degrees. And this is in amps. So BC is equal to 13.8 angle of minus 36.9 degrees minus 120 degrees. That gives me IBC is equal to 13.8, magnitude never changes because it's a balanced system, minus 156.9 degrees, and this is in amps. And last but not least, 13.8, angle of minus 36.9 degrees plus 120 degrees. That gives me ICA is equal to 13.8, angle of 83.1 degrees. And this is in amps. I drew the phasors for you on my on my solutions. I'm not gonna do it because wait, I'll give you that answer. Here, okay. Now, say you came up with all this. This exam, and you finish the exam in 1 hour, and you have almost 2 hours to go, and you're like, I finished the exam. That last problem was, before I give my exam, I want to make sure that my answers are potentially right. One way to prove it to yourself is what you got. If these phasors are right, one way is if you add this voltage plus this voltage plus this voltage, you get something close to zero. If I add this current plus this current, you should get something close to zero. When you do it on the calculator, you know how you take 83 point something angle? Sometimes you don't round out. You might end up with a very small angle, a very small negative magnitude. It's zero. So if you add them among themselves, because it's a balanced system, this plus this plus this should be close to zero. This plus this plus this should be close to zero. This plus this plus this should be close to zero. And then this plus this plus this should be close to zero. Okay? In this configuration, if the current is not in the configuration with the Y, where it's a Y and a Y here, the current flowing through the neutral, if one of these magnitudes was a little larger, let's say this is 28, same, leave everything the same, just change this to 28, you're gonna get, when you add this, you don't get zero. If it's a Y configuration, that current flows through that neutral. Okay, the X is current. And you might say, what happened here is when I have that? The current is circulating here. The current circulates in the delta. Okay? So that's the case. But that's beyond. Does it make sense, everybody? All right. I'm glad that I skipped the problems. The other problems, they're similar. I'll give you all the answers. You can review them one by one. Can you please upload your homeworks? I think they're all of them are there. How about if I give you until, if you have not, upload them, because you can use this to practice for the exam. If you if you don't have them, you want to upload them after the exam forward, I'm okay with that, but right after the exam, so I can take exam one and the very first 4 homeworks and grade them, so I can enter my scores. If you have any questions, please, I see a lot of people were missing, I hope, if you see everybody, just tell them what I talked about, right? I don't like it because I've been, I missed it. But if you don't have any questions, I'll see you next week. As I said, I'll give you the whole, don't forget to write your cheat sheet, don't